Well, hello everybody. What I need to do today is I need to cover section 2-4 with you. It's over exponential growth and exponential decay. It should really be reviewed from both your Advanced Algebra 2 days and your FST days. We had a whole lesson on this day in FST. If you're missed, instead of doing this video after our quiz, we did take a quiz today, which I call a grade-raising opportunity. And then your assignment's going to be on Math Excel. So let me jump right into the lesson. Let me define for you what an exponential function is going to be for us. An exponential function is going to be of the form ab to the x. So I have some number out front, I have some growth factor, and then it's going to be to an exponent of x or t, whatever we're dealing with. What makes it an exponential function is our unknown is part of the exponent. A little trip down memory lane. If b is greater than 1, it's going to represent exponential growth. And if b is between 0 and 1, it's going to represent decay. We do not allow b to be negative because if it did, our graph would jump like this. So our graph would look something like that. So b can't be negative. On this slide, I just put a couple of examples for you. 3 to the x. This would be an example of growth because my b value is 3. My a value would be 1 since there's no number out front. On this one, it would also be an example of growth. 1.02 would be an example of growth. In this case, my a value would be 4. My b value would be 1.02. This would be an example of exponential decay because my b value is between 0 and 1. So if you would come over to your example 1, what I'd like to do is sketch a graph for you to represent growth, and then I'd like to talk about the domain, the range, the intercepts, and all that good stuff. So here goes. I'd like to show you what a graph of an exponential growth function would be. So I picked a graph of f of x equal 2 to the x. You are welcome to graph this in your calculator. It's going to be faster just to do it in our heads. So check this out. I'm going to let x be 0. And if I let x be 0, I'm going to get a y value of 2 to the 0, which is 1. So at 0, I've got 1. If I let x be 1, 2 to the first is 2. If I let x be 2, 2 squared is 4. If I let x be 3, 2 cubed is 8. Now let me go back the other way. Let me let x be negative 1. So I have 2 to the negative 1. Remember our rules of negative exponents? That's equivalent to 1 over 2 to the first, so 1/2. If I let x be negative 2, I'm going to have 1/4. So guys, our exponential growth function will look something like this. Some facts about it. The domain will be negative infinity to infinity. Our range will be 0 to infinity. This graph will never cross the x-axis, no matter what value you pick for x. No matter how small that is, how negative it is, it'll still be a little bit above the x-axis. In this case, my intercepts occurs when x is 0. In this case, it's 0, 1. Now, if you only focus on ab to the x for a second, if you plug in a 0 for the x value, b to the 0 would be 1. 1 times a would be a. So you'll always have an intercept at 0, whatever the main number is out front. This thing we're going to say is strictly increasing. Now in behavior, I'll slow down just a tad on. I got to do this. I got to say as x approaches infinity, f of x does something. And then also as x approaches negative infinity, f of x approaches something. So based on class last time, as you look to the right, notice my y value seems to be going up, up, and away. So infinity. As you look to the left, though, it's approaching 0 this time. Last time it was approaching infinity or negative infinity. So there's an example of exponential growth. Let me come to the next one. an example of exponential decay, I'm going to pick on the graph of 1/2 to the x. It could also be written 2 to the negative x. I just wrote it this way because it looks easier. I'm going to do the same thing I did, guys. I'm going to let x be 0. 1/2 to the 0 is going to be 1. If I let x be 1, 1/2 to the first is 1/2. If I let x be 2, I'm going to have 1/4. If I let x be negative 1, though, that's going to be equivalent to 2 to the first. So at negative 1, I've got 2. At negative 2, I'm going to have 4. At negative 3, I'm going to have 8. So guys, my exponential decay model looks like this. Some facts about it again. The domain, negative infinity to infinity. Our range, 0 to infinity. Our intercept in this case is at 0, 1, or 0a if you're graphing something different. We'll say this thing is strictly decreasing. And then once again, the end behavior will look like this. As x approaches infinity, f of x approaches something. And then also as x approaches negative infinity, f of x will approach something. We just got to go fill in those somethings. As I look to the right, I'm approaching 0. As I look to the left, I'm approaching infinity. So there's what we got going on so far. Now, on your next little slide here, guys, sorry about that, little break in the recording. What I'd like to do here is just roughly sketch what each of these graphs would look like. Part of the assignment in Math Excel today, you'll be doing a little bit of matching like we had in the book a little bit. So if you think about 2 to the x minus 3, this is going to shift our regular graph of 2 to the x. It's going to shift it down 3 units. So instead of having an asymptote at y equals 0, I'm going to have an asymptote at y equal negative 3. It's going to take that normal point that was at 0, 1, and it's going to move it down 3 units. So it's now going to be at 0, negative 2. And I'll just label that for you. So there's what that graph's going to look like. Now, if you look at our f of x is 2 to the x plus 1 minus 2, here's what's going to happen on this graph. This minus 2 is going to move it down 2 units. Now, if you look at that exponent, the exponent is a grouping symbol. That x plus 1 is going to move it left 1 unit, just like it would in a parabola if it was inside the parentheses. So I'm going to take my normal point that would be at 0, 1, and I'm going to move it down 2 and over to the left 1. I'll have an asymptote right here at y equal negative 2. And my graph's going to look something like that. If you look at our third one, that negative out front, instead of opening it this way, we'll simply open it that way. Just like if it was a parabola. Parabola being positive would open there. Put a negative inside of there. It's going to open it downwards. Now, this one's a little trickier. Here's what this one's going to do to us. It's going to move our point up 3 units. It's going to move our point up 3 units. So I'm going to have an asymptote up here at 3. This negative out front is going to make it open like this, but this negative exponent is going to flip that. So this is going to look something like that. Don't worry, I won't take your calculator away from you, so you could always graph it and get the shape of it. Okay. Now I'm going to switch gears just a little bit now, because I need to show you what or how we're going to solve exponential equations. We're going to solve these exponential equations with a method called the common base method. In the common base method, we want to get a common base. So here's what I mean. Look at 4 to the x equals 64. I'm going to ask myself if I could write 64 as a base of 4. If I can, good for me. If I can't, we got to work on both bases. Well, I'm going to think of this as 4 to the x. I'm going to think of 64 as 4 to the third power. Once our bases are the same, I can just work with the exponents. In this case, x is going to be 3. If you look at 3 to the x plus 1 equal 81, I'm going to try to write 81 with the base of 3. So I've got 3 to the x plus 1 equal, I'm going to write 81 as 3 to the fourth power. Well, now that I have that, work only with your exponents. X plus 1 equal 4. So in this case, x must be 3. So we're trying to get a common base. I'm going to come down and look at number 7 first, and then I'm going to come back and do number 6. Notice that I can't write 32 as a base of 4. But they both have a common base of 2. I could write 4 as 2 squared. I could write 32 as 2 to the 2, 4, 8, 16, 32, the fifth. Now notice that there's still an x there, and there's still a 4x minus 3 there. But the big thing I just did, guys, I got a base that's now the same. If I work on this, this now becomes 2 to the 2x equal 2 to the 20x minus 15. What did I do there? A power to a power, you multiply your powers. So that's what I did there. Now my bases are the same. So I'm going to set the exponent equal to each other. And then we're just going to solve this. Subtract 20 to both sides, so I've got negative 18x equal negative 15. Looks like x is going to be negative 15 over negative 18. So it looks like it's going to be 5/6. Now I'd like to come back up to number 6 now. Notice I got a 1/2 and an 8. Well, the common base between those two is going to be a 2. But I'm going to rewrite 1/2 as 2 to the negative 1 to the x minus 1 power. And I'm going to write 8 as 2 to the third. Let me simplify what I have now. I'm going to have 2 to the negative x plus 1 equal 2 to the third. So once again, I just multiplied my exponents. A power to the power, you multiply your exponents. Now when I work with my exponents, I've got negative x plus 1 equal 3. If we solve this by subtracting 1, the opposite of x equal 2. So x must be negative 2. So that's how we solve them with the common base. Number 8 won't be bad. Between a 125 and a 25, it looks like a 5 is my common base. So I'm going to think of 125 as 5 to the third to the 3x equal 5 squared to the 2x plus 5. So I got my base the same. So this becomes 5 to the 9x equal 5 to the 4x plus 10. Now we'll just go solve this. I've got 9x equal 4x plus 10. Subtract 4x. Divide by 5. Looks like my answer is going to be 2. If I peek on over at number 9, I don't care what the base is. We'll talk about e later on in this video. But my base is already the same, so I need to set x squared minus x equal to 6. Well, since that's a quadratic, let's set that thing equal to 0. X squared minus x equals 6. Let's factor this into x minus 3 and x plus 2. So in this case, I have two possible values. I could have positive 3 or negative 2. So there's how we solve exponential equations using a common base. Next time we'll look at logarithms. Now, I wanted to slide in here. Our book still kind of called them exponential equations. I'm going to call them non-exponential equations, but they show up in this chapter a little bit, so I'm just going to review with you how to solve those. This isn't an exponential because my unknown isn't in the exponent. So I've got x to the 3/2 equal 27. When this happens, I'm going to raise both sides to that reciprocal power. So instead of 3/2, I've got 2/3. I'm going to do that to both sides. Now, if you check out what's happening on the left-hand side, a power to the power, you multiply your exponents. I'm going to have x to the 3/2 on 2/3 is really just x to the 1st. Now, I need to figure out 27 to the 2/3. So I'm going to go back a chapter. This is really the cube root of 27 squared. So this is really 9. If you look at number 10, I need to get that x to the 23rd all by itself first. So I'm going to divide both sides by 3. So I've got x to the 23rd is 200. So some number times itself 23 times is going to get me close to 200. I'm going to raise 200 then to the 1/23rd power, the reciprocal of that, and get approximately 1.26. Here's my number 11. 1 plus x over 4 to the 12th equal 531,441. I need to get rid of this 12 first. So I'm going to raise both sides to the 1/12. Well, when I do that, on the left-hand side, I've got 1 plus x over 4. On the right-hand side, if you run that through your calculator, you're going to get 3. Now we're just going to solve this. I'm going to subtract 1 from both sides and get 2. I'll cross multiply and get 8. So guys, there's how we're going to solve non-exponential equations. That'll come in handy when we do our logarithms. Now this should be review from your Algebra 2 days, guys. Compound interest formula. I've listed it there for you. A equal capital P 1 plus R over N raised to the N over T. Just to make sure that you remember what everything is. A represents the amount in your account. P is the original investment, called the principal. R is your interest rate as a decimal. N is the number of times your money gets compounded. In theory, the more times the bank compounds your money, the more money you make. We talk more about that coming down the road. And it's raised to the power of the number of compoundings times the number of years. And that'll yield us our total number of compoundings over the life of the loan. So it's going to look like this. Assume that Lisa invested $2,500 in an account that pays 5.5% interest. Oh, that would be nice. For 3 years. How much would be in her account if compounded? Well, guys, it's going to look like this. The amount that I would have in my account in 3 years could be found by 2,500 times 1 plus the interest rate as a decimal, 0.055, over 4, compounded quarterly, raised to the 12th power. And I got that 12 by going 4 times 3. And guys, if you run that through your calculator, you're going to have that Lisa would have $2,945.17. If you want to make sure you can run it through, you can always pause the video and then get that kept going. The only thing that's going to change if it's monthly, I could do this. The amount after 12 months, or the amount when compounded monthly, could look like this: 2,500, 1 plus 0.055 over 12 raised to the 12 times 3 is 36. So we made the decimal smaller, but more compoundings. And if you run that through, you should get $2,947.37. Notice that we compounded the money more, so your interest made interest faster. Now, I'm going to come back to continuously here in just a little bit. And I'm erasing that so when I do come back, I got room. So I'm going to come back and do continuously and that 12B. So, believe it or not, guys, the video is getting close to done. Here's my number 13. Hoping to retire with $1 million in my bank account, I have invested $20,000 into an account that compounds my money quarterly. When I retire in 7 years, oh, I wish, the money will have been in the account for 25 years. What interest would I need to be paid to have my $1 million? And really, as I read that, that should be what interest rate would I need to be paid to have my $1 million? Well, what I'm going to do is take that formula again, and let's plug in $1 million for the amount that I would like to have. We're originally investing $20,000. I've got 1 plus. I don't know the interest rate that I need, but I do know my compoundings is 4. Now, when I retire in 7 years, the money will have been in the account for 25 years. So my exponent here is going to be 100. Now, to solve this, what I'm going to do is I'm going to divide both sides by 20,000 first. And when I do that, I get 50 equal 1 plus r over 4 to the 100th power. Now, we did one of these earlier. To now solve this, I need to take 50 to the 1 over 100th power, and that's going to be equal to 1 plus r over 4. Now, I'm going to run this continuously through my calculator, but when I go 50 to the 1 over 100, I get about 1.039895503 equal 1 plus r over 4. Well, I need to solve this thing for r. So we're going to subtract 1 from both sides. So I'll have 0.039895503 is equal to r over 4. And then to bring it home, I'll need to multiply by 4. So unfortunately, for me to have $1 million in my account after investing $20,000, my interest rate's going to have to be 15.958%. So my interest rate's going to have to be approximately 16%. So chances of me retiring with $1 million, slim to none. Okay, really kind of my next to the last part here, guys. Video is going to be about 28, 29 minutes, so not bad. Hey, I want to introduce you to the concept of E. E is the number that represents continuous change. It's really a cool number, and it's really neat how it came about. A guy named Jacob Bernoulli, he discovered E. And how did he do that? He did all this by hand that we're going to do on our calculator. Took him many, many, many days, because it's just really, he just sat down and grinded it out. But here goes the thinking. Given our compound interest formula, he only wanted to think, hey, what happens just in a year? I don't want to think outside of a year, but I just want to think about a year. What if we could compound money as fast as we could? So here's what he did. He says, I'm going to invest $1 for 1 year. but I'm going to let my interest rate be 100%. If you think about bacteria growing and such, that's where this comes in hand at. Well, so here's how we start getting these money. So for this first one, it's going to look like $1, 1 plus 1 over 1 to the first. Well, that's an easy one. 2. To do semi-annually, it's going to look like 1 times 1 plus 1 over 2 squared. So when we do that, that's going to be 2.25. Let's look at quarterly. It's going to look like 1 times 1 plus 1/4 to the 4th. Kind of see the pattern here? That's going to be about 2.44. And then, guys, he's doing all this by hand. His next one was 1 plus 1 over 12 to the 12th, and that came about 2.613. He did daily and got about 2.714567, and then he went hourly, minute, so a lot of hand time. But guys, you have a E button on your calculator. If you would find that and go second e to the x and let x be 1, and you're going to see that e is approximately this value right here, 2.71828, 1828. It's kind of like the number pi. It goes on forever without true repetition. Now, where does that come in handy at? If you take this part of your formula, the 1 plus r over n to the t, where t is 1, and I'm going to change that to an n, this part comes out to be that e number. So see if this formula sounds familiar for continuous change. I remember it because there's a shampoo that looks like this in a green bottle, but the amount that you would have is given by the principal, e to the rt, so pert. So now, hang with me for 2 more minutes. Come back to Lisa now. I'd like to figure out how much money Lisa has in her account if the bank could compound it continuously. So her amount now would look like this. The amount that she would have would be $2,500. E to the interest rate that we was dealing with, 0.055, times, in this case, how long were we leaving that in there? 3. If you run that through your calculator, make sure your calculator puts that in parentheses for you, and you should get right at $2,948.48. Compare that to that. Notice it's a little bit more. Okay? So guys, that's going to finish up my video. Assignment-wise, it's going to be out of Math Excel. So good luck on that, and let me know if you have any questions.